Okay, it's my great pleasure to introduce our speaker for today, Fiodar Kazhamiaka. Fiodar was actually my PhD student at the University of Waterloo. And before that, he was my master's student. And before that, he was an undergrad working with me. So he's been working sort of with me for the last decade or so. And currently, after doing a postdoc at Stanford with Matej Zaharia and that research group, he's at Azure Cloud. He's sort of halfway between the deployment people and the research group. And he's going to tell us today about some of the research challenges as we try to build a cloud computing infrastructure that wants to become net zero, as Microsoft's ambition is, especially when it invests in ChatGPT. So let's find out about that. So Fiodar, I should add, it's 5 a.m. for him. So he's really, he's going over and above. So thank you so much for doing that. And we're looking forward to your talk. Thank you.
Thanks, Keshav, for the introduction, and please excuse me if I get off to a slow start. I just started drinking tea, so I'll ramp up as I go. Yeah, so Keshav actually said everything I wanted to say on the title slide, so let me move on. The goal of my talk really is to share what I learned since I've joined Microsoft, which was only about 6 months ago. I joined as a new researcher, and my goal really, the goal of my orientation was to understand what people at my research group has done already, what kind of opportunities there are for me to improve the efficiency and sustainability of the cloud platform that we're working on. And so along the way, I asked a whole lot of questions and got a lot more answers than I bargained for. And I tried to create a talk to hopefully share all I'm allowed to share with the academic community, right? So that's the goal of this talk. I'll be covering a really wide breadth of topics because there's a lot that goes into building a cloud like Azure. And so one of the primary goals is really to, rather than going deep into a specific research topic, I really just want to engage you guys around many different topics and hopefully discuss stuff. I only have about 30 slides, so I'm betting on some discussion and interaction during this presentation. Right. Also note that a lot of the things that I describe will be sort of qualitative, and that's usually because I can't share exact numbers. So please excuse me for that. Just to start by honing in some terminology. When I talk about the carbon emissions of the data center, it's going to be split up into 3 scopes. Scope 1 is all the kind of direct emissions that we do on site. So anytime we have to burn diesel to run a backup generator or burn fuel to run some machine in the warehouse, that's scope 1 emissions. And those tend to be actually really, really small piece of the overall emissions that we're responsible for. Scope 2 is a much larger set of emissions. That's all the emissions that come from producing the power that we use to power the building and run our data centers. And then scope 3 is all the kind of embodied carbon in all the stuff that we had to acquire in order to build and run the data center. So anything from kind of all the supply chain of the steel beams that build the data center, the chip manufacturing process for all the chips that make up our CPUs and SSDs, all of that goes into scope 3. And so scope 2 and 3 are really the biggest aspects of our emissions, and that's what we're going to target reducing. And that's exactly kind of what Microsoft has committed to doing. What I'm showing you now is a timeline of all the kind of publicly stated goals of Microsoft when it comes to reducing their emissions, where by 2025, they want to have actually built enough renewable energy capacity to offset 100% of what we use. Now, it doesn't mean that they built a power plant right next to the data center, right? It means that maybe we built a wind farm in Texas to offset the energy that was used in California, right? it doesn't have to be necessarily time aligned or spatially aligned. So that's the goal for 2025, is just to be putting money towards building renewable capacity worldwide. Okay. They're actually going to improve on that by 2030. And there's a lot of goals that we're trying to meet come the end of this decade, right? We actually want to have spatial and temporal matching of our renewable energy investments. So this is known as this 100-100-0 goal, which means that 100% of the time, 100% of the energy that we use is going to be zero carbon. And I'm kind of saying zero in quotations here because even solar and wind is not totally carbon free, but compared to some of the conventional sources that involve burning fossil fuels,
Peter, I think we may have lost you because for some reason my computer seems to have lost Wi-Fi and regained it. So could you just repeat the last minute or so? Sorry about that.
The last minute. Uh-oh.
You talked about 100% built renewable energy capacity, and then we lost you after 2025. Yeah.
Did I finish that point? Perfect.
Yes, I think so. Yeah.
Okay. So come 2030, we actually want to not just build that renewable energy capacity, but match it both spatially and temporally. And that's known as this 100-100-0 goal, where 100% of the time, 100% of the energy we use is supposed to be zero carbon. Okay. And so zero carbon refers to essentially running on renewable energy, which isn't exactly zero, but it's very, very close relative to kind of conventional burning of fossil fuels. Yeah. Over on the top here, we also hope to reduce our scope 3, all the supply chain emissions, by more than 50% relative to what it was in 2020. Right. I'll talk a little bit about how we're moving towards that. And then in that same year, we actually want to be in the business of removing carbon. So all the carbon that was emitted that year, right? Suppose we manage all of scope 2 with renewables, we have all this scope 3 left and a tiny, tiny little bit of scope 1 emissions. We hope to remove all of that through various means. And I'm not super well informed on how we're planning to do that. And actually, Keshav, you and your research group might have a better sense of how to do that. But then come 2050, the very long-term goal, it's hard to project that far, but is actually to remove all the carbon that has been emitted historically since the founding of the company in 1975. So this talk is really going to focus on a subset of these 2030 goals, which is trying to reduce scope 3 and then shifting towards this 100-100-0 model for renewable energy, where we actually have spatial and temporal matching. So thinking kind of broadly about where we'll be if we achieve kind of the very first goal, right? So currently scope 2 dominates our carbon emissions. The fossil fuels kind of that are burned and emit a bunch of carbon into the atmosphere power a lot of our data centers and dominate our emissions. But if we succeed in kind of meeting our goal in that regard, we're going to see this shift towards scope 3 dominating the emissions. And so we really have to start thinking about the supply chain, how things like how long we use our servers before they're decommissioned, those start to become kind of the dominant area under which we can further find carbon reduction, right? And it's still going to be important to reduce these emissions because unless we have a radical breakthrough in the technology for removing carbon from the atmosphere, it's still going to be expensive to do so. So if we want to meet our goal of net zero efficiently, economically, we're going to try to reduce our scope 3 as much as possible, so we don't have to pay a lot of money in that regard. Right? But even achieving something like this 100-100-0 goal is going to be really difficult. And I'll talk about a little bit about that later in this talk. And so why does it make sense to focus on Azure emissions? I remember having a conversation with you, Keshav, about why you don't work in this space, because you're a computer scientist who's interested in sustainability, and it felt to me like there were a lot of opportunities here. And your answer was, well, basically, data centers make up this really tiny fraction of world energy consumption. As a reason for maybe focusing on other sectors like transportation, for example, where you can make a really big impact. In my view, and when I talk to people, at least at the company, they see 1 to 2% as actually a very big chunk and a very important chunk of the puzzle, because these workloads are rapidly growing, right? Clouds are projected to grow at a rate of 25% year over year for the next 5 years at least. And then we have this new workload that might actually increase that pace, right? Everyone is really excited about AI. And AI is a very, very compute intensive workload. And nowadays we want to put it into everything, right? So to us, that's like a huge growth opportunity. What that means is that 1 to 2% might grow to be 10% if we're not careful, right? And we want to keep that number down. Another reason for this is that sustainability kind of over the last decade has been accompanied by this business case, this short-term business case, where it actually makes sense to focus on sustainability in order to grow your business in a capitalist economy, right? And I think most companies that have kind of public-facing brands where their business depends on how their company is perceived has noticed that, well, young people really care about sustainability. And so we need to be seen and viewed as a sustainable company, or we're not going to be able to grow as well as our competitors in that market, right? I think this is what allows Microsoft and Azure to hire researchers like me that care about this stuff, because it makes sense. Like, sure, maybe my hiring manager also cares about sustainability, but the bottom line is always really what matters. And right now, the bottom line is going to be affected by how sustainable Microsoft really is, right? So it's a great time to work on, at a place like Azure, on sustainability-related topics, because we have a lot of support throughout the company for improving in that regard. And then there's this other aspect. So the cloud is essentially dominated by 3 big players, right? Amazon, Google, and us. And we're all constantly looking at each other to see who has kind of the latest, best idea in this regard, and copying each other when someone has a good idea, right? It's really a race to the bottom in terms of margins for cloud platforms. And so just really, if I'm able to convince the right person at Microsoft to implement some research idea that happens to make a big impact just for Azure, right? It'll quickly spread to every cloud provider, right? And so one person can really have a major impact in this space and on this 1% of energy consumption and carbon emissions. Very briefly about kind of Azure, right? We exist in 59 regions around the world. It's hundreds of data centers, and it's over 4 million servers, okay? A lot of computational capability that we're working with, and a lot of potential to cause harmful emissions, right? Not to mention building 4 million servers and hundreds of data centers. Okay. So how does the work that we do in my research group kind of help Microsoft progress towards those 2030 goals? And I've tried to break down the stuff that we've worked on into 6 categories. And mind you, I only got here recently. So most of what I'm talking about, I have had no impact on. And it's work that has been done recently by my colleagues, or we're planning to do in the near future, right? So resource and energy efficiency are all about doing more with less, essentially. And there's also this angle we can play with as systems researchers, where we build systems to actually enable them to be powered by renewable energy. I'll talk a little bit about concrete projects and deployments that we've done to facilitate more renewable energy on the grids that we operate in. Extending hardware lifetime, it's kind of its own bullet point because of how important it is to the scope 3 carbon. And I'll explain exactly what I mean there. And then there's this opportunity to really redesign how data centers and servers look like, right? You know, when the cloud was first built, right? When Azure was first built 10, 15 years ago, it wasn't perfect, right? The goal was to get something up and running, right? To be a player in this new space. And now we have all of these legacy systems that could totally be redesigned to be more efficient, more sustainable. And we have the prerogative to look at these sort of problems and create suggestions for how those designs might evolve as we build new data centers or reprovision old ones. Right, so all of these research topics are things that we touch at the research group, and I have things that I want to share with you guys. There's going to be a slide on the research opportunities for every one of these, hopefully to capture your imaginations a bit. So this slide, I'll start with talking about research efficiency and focusing particularly on power infrastructure. And this slide shows what the power infrastructure looks like at a data center. So if you start at the very top, you have kind of some utility line that feeds in and splits off into a bunch of transformers. And there's 4 pictured here. Every transformer feeds into a UPS, and there's also a generator. These Gs represent typically diesel generators that are used to provide backup power in the event of either a utility failure or a failure of one of these transformers. The UPS also actually has a battery, typically lithium ion, that is used to quickly provide a lot of power for a very short duration in the case of an outage during the time it takes to ramp up one of these generators. So we're talking a few minutes of battery capacity at a very, very high power output, right? Enough to sustain that section of the data center for a few minutes. And then each UPS kind of splits off and powers portions of different rows in the data center, where each row is just a bunch of racks and each rack is a bunch of servers. Okay, I'll pause here for any questions about this diagram. Okay, great. And one thing to note is that there's essentially what's called 4n/3 redundancy built in here, where if one of these goes down, if one of these transformers or UPSs, generators, batteries goes down for whatever reason, there's 3 more that can pick up the slack and cover its load, right? And so one thing that's important to note about Azure is that we provide one service level agreement to our cloud clients, and will be available 99.999% of the time. We call it 5 nines availability. And the way we achieve that is by putting in redundancy, things like this 4n/3 hierarchy, so that when the grid, which is not 5 nines reliable, goes down, or one of these individual devices, which is not 5 nines reliable, goes down, we have something to pick up the slack and continue operating. Right. So one opportunity just from what I showed you is it comes from this amount of reserve power that I talked about, right? In order to maintain that reliability, we have some amount of power capacity that is essentially reserved only for emergencies, right? This is infrastructure that's been built out, but is underutilized, really. And this graph on the right kind of shows that we might have, at any point in time, this green bar represents all the power that's utilized by the data center. And then this white area represents some amount of slack that maybe we'll be able to fill in by putting more VMs on our existing machines. But at no point will our total utilization, power utilization, exceed kind of where this white part of the bar stops. The rest is just reserved for failovers. All right, great. Here's an idea. Why don't we utilize that backup area and serve VMs that don't require that 5 nines reliability? Workloads that we can actually lower the frequency of their CPUs and get power back from those VMs in the event of a failure, right? So not all workloads that run on Azure require super high reliability. A lot of things really don't mind if we throttle them, right? Especially if we allow those workloads to run on a cheaper kind of VM instance, right? Because we say, fine, you're allowed to kind of place a VM on our machines and exceed kind of this part of the capacity, go beyond this 75% cap. But if there's an emergency, we're gonna throttle you, right? For as long as it takes for us to recover that capacity. And there's a lot of carbon benefit that comes from being allowed to take advantage of this, right? It's essentially a resource that was previously unused but built, right? And so we're able to stuff more VMs into a single data center and amortize from all the non-compute infrastructure that we have, things like power, cooling in the building. So how much of these workloads do we really have? Might be kind of a natural question to ask. And here's a breakdown of the workload distribution across 4 Microsoft regions in terms of how flexible they are, or how susceptible they are, or how ready are they to scale down. And so a large portion, right, at least 20% of our workloads is actually software redundant, which means that, you know, there were good engineers that built a good distributed system to power, say, Bing, right? Bing doesn't care if a bunch of servers go down because all of its other servers can pick up the slack and hopefully nothing critical is lost, right? So that's what software redundancy means. A huge portion of workloads, somewhere 20 to 40% of it, are actually power capable, which means that they're probably not user facing. They don't have strict latency requirements. You know, it's not like the web server for Bing. It's going to be something that recomputes indexes once in a while, batch jobs, something that can take a hit in the CPU frequency if need be for a very short duration while we recover some power. A lot of workloads actually fit the bill for that. And then we have some workloads, maybe 20 to 40%, depending on which region we're looking at, that we can't touch. This is going to include, by the way, all of our cloud clients, right? The ones that we provide this 5 nines reliability to. One important thing to note here is that Azure doesn't just run public cloud facing VMs. There's a host of kind of internal production stuff that makes up a huge portion of the workloads that run on Azure and that we actually have insight into, right? And so I can go to someone like Bing and convince them to participate and make their VMs capable, right? And say, well, we'll kind of like charge you less funny money to run on our servers, right? And it'll increase your budget, but you have to let us throttle you, or specific VMs, okay? Right. And just a quick graph showing what we used to do before when it comes to kind of power used over time. On the left is what the picture was beforehand, where over time, we have to essentially make sure that our power usage doesn't go above 75% of total built capacity, because when there's a failure, a single failure might drop 25% of capacity, it doesn't affect us. And when we recover, nothing happens. With this system that allows us to cap servers, we call it Flex, we're able to exceed this 75% threshold. And when there's a failure that causes some amount of capacity to be lost, we very quickly ramp down those workloads and then can ramp them back up, essentially allow those CPUs to increase their frequency back to what it was when that failure is recovered. Okay. Any questions here?
If I can, so Fiodar, I mean, this reminds me, takes me back 30 years. This is almost exactly what was proposed for the internet back in the early 90s. It was called guaranteed service, but it called non-capable and best effort, which is this power capable and so-called variable bitrate service. And so this whole issue of admission control, how many jobs can you admit? How to make sure that you can degrade jobs, degrade the video quality of MPEG, for example, to reduce its bitrate. It's exactly analogous to what you have over here. So not online, but we should talk about this because there's a lot of very good research done between, let's say, 91 and 95 or 97 about this kind of stuff.
Awesome. Yeah, it'd be great if there are some insights. I can't remember the last time I read a paper from 91 to 97. So.
Right. Yeah. So this is reinventing some parts of some old genes. And he's nodding his head. He was around.
I did the management-based edition. That was nice.
Yeah.
Can I ask a question?
Yes, absolutely.
So my question would be, if I look at the graph above, I would infer that the power capable and the software redundant parts are the ones that you have insights, because these are Microsoft workloads. What would you say in terms of ambition for Microsoft is to try to explore different interfaces so that even for the tenants, you may recoup power capable VMs?
I don't know how to characterize ambition, but it's certainly something that we're really interested in exploring. Finding ways to allow our cloud tenants to expose their flexibility is something that will kind of allow us to unlock this top bar. And so we're seriously interested, and we have a lot of support from all of the kind of internal workloads that we talk to try out kind of having interfaces that we would later expose to our clients to let them tell us, like, hey, this is a workload that you can cap, or this is a workload that you can scale it down somehow if need be, or ramp it up when there's more opportunity to do so. Yeah.
Okay, thank you.
And unfortunately, I don't have a ton of information to share. I think a lot of people have been thinking along these lines of how to expose this to our cloud clients. And it's an uphill battle in some sense, because a lot of times people enjoy having this 5 nines availability, even if they don't need it, because that's what they're used to. Right now, slowly, all of these companies care about sustainability. And if we're able to demonstrate that maybe by having them expose this to us, we're going to be able to reduce not just our carbon emissions, but what's in their accounting, right? Because they have to account for the carbon emissions to do with their workloads in their carbon accounting notebooks. So I think there's going to be a strong case for us working on this.
But I got a question that sort of follows up a little bit on that one. So those people that enjoy the 5 nines and all of that, actually, this is another one where it seems that we're following a bit of past history. One of the, I think Dave Patterson used to describe programmers as the lazy boy programmers, just as lazy boy chairs. And with respect to multi-core and distributed systems in general, but it was a real comment about how they had to make assumptions about the reliability of the underlying system. And so they made the ones that made their lives easiest. And I'm wondering if the 5 nines and so forth is the networking or data center instantiation of that. And perhaps the way forward is to be more embracing of data center support for unreliable networks.
QoS, this comes back again.
And Keshav will tell us everything was invented 30 years ago. I will actually counter him with, no, it was invented 70 years ago, but that doesn't matter. So is there any efforts in the great provider in the sky to look to encouraging its development of APIs and support infrastructure and so on that is much more supportive of the apps that you need for the power flexibility?
I would say there's some focus on that, not as much as I'd like. For example, I can point you to Azure documentation, which tries to point developers to various ways that they can write more sustainable code so that their workload is more sustainable, right? I don't think that's like the best way forward. I think it would be great if the platform can take care of most of that and we can actually support lazy programmers.
Do you perceive that it's going to be synthetically pretending to be 5 nines reliable or somewhere in the middle?
I think if we promise 5 nines, we'll have to keep it, because no one's gonna be tolerating some of our bigger clients calling us and saying, what the heck happened to our workloads? The key point is going to be to find incentives to move people away from that model, right? And we can do it, right? There's reason to do it because we can actually save money as a platform if we don't have to maintain 5 nines reliability for everyone. So why don't we decrease the price, right, of a certain class of VMs that has low reliability? And we're actually doing that. There's a concept of 3 nines reliability for a lot of new workloads that we're sort of working towards. That paper hasn't been published yet, so I don't want to talk too much about it. But we're trying to convince right now internal workloads, those that are, for example, software redundant, to move towards a 3 nines reliability model where we can actually shut them off entirely, not just cap them, shut them off, right? And they'll come back online, and we can do that, I don't know, 0.1% of the time per year they'll be off. But doing that unlocks a whole bunch of things that we weren't able to do before. Okay. So we're moving that direction. All right, I'll move on. When it comes to resource efficiency opportunities, I'm not going to talk too much about the power infrastructure, but more on the CPU as a resource. Yeah. So on average in Azure, we have 70% of our cores, they have VMs allocated to them. That means someone is paying us to host a VM on those cores. And an average of 70% is actually really, really good. I think it's higher than kind of our competitors, just because of fluctuations, even over the course of a day, and demand for computation. So it's going to be hard to increase that number. But what's somewhat easier to increase is utilization, right? Just because a VM is assigned a core doesn't mean it's actually using it. And so right now, you know, the one public data point that I found that I can share is that roughly 75% of VMs have less than 25% CPU utilization. And if you run the numbers on this, you'll see that means that more than half of all cycles are idle. And it's a lot more than just half, I promise you, right? So across 4 million servers, that's a ton of opportunity. And I want to stress this point. Even from a kind of sustainability point of view, these idle cycles are still consuming a lot of power. We would prefer for them to not be idle because of how non-power proportional these systems currently are today, right? We would rather be doing some amount of work, even if we're paid less, right, to do it. One note on this is that, an easy solution might be to just say, well, if you have so much idle cycles, why not just oversubscribe more, right? Why not stuff more VMs into a single machine until you're able to see kind of much higher average utilization? It's really hard to do this, especially when we have these clients where we don't have a lot of insight into what their utilization will be like a second from now, right? We do have a ton of modeling. We have like ML models for like every VM that comes online, where we try to guess what their profile is, and we use that to make somewhat better decisions on oversubscribing. But even with those models, right, we're seeing this point that I have in blue. A ton of cycles are left on the table. There's been another kind of direction that we've tried to go in order to increase these numbers, a class of VMs that we call harvest VMs. I don't know how familiar you guys are with harvest VMs, but essentially it's a VM where you maybe pay for a minimum of 4 cores. And so you'll get 4 cores allocated to you. But if there happens to be 20 cores available on that VM that are unused, even if they're allocated, they're not being used at a particular time, that VM will get a chance to use them, right? And if someone else then wants to use their allocation that they paid for, the harvest VM will scale back down to a minimum of 4. So it's essentially a workload that tries to grow out and use the available cycles. Right now, a small fraction of all the VMs that we run are harvest VMs, despite this being something that's been built out for several years. And I think a large part of that, why it hasn't grown, is because there aren't a whole lot of software tools that allow people to take advantage of resources that scale up and down kind of without having ever control over them, right? It would be great to have things like libraries that quickly kind of scale out some kind of multi-threaded computation over many cores as they're available, and then back down. And this isn't like something that happens very often, right? We see harvest VMs that scale out to 20 cores and last like that for hours, for days, until they have to give them up, right? And that person that bought that harvest VM was really only paying for 4 cores plus a little bonus in order to be able to harvest the rest that are available. But it's about having kind of the tools out there to build tasks that are able to take advantage of this opportunity. And I think we're lagging in that respect. This would be interesting to have people be more aware of this and to maybe build them for us.
Can I ask a silly question? What's the service level agreement you give about CPU usage, right? It sounds like it's in terms of dedicated cores, like it will appear to you that you have n dedicated cores, but doing that's not the only way that you could do that.
Sorry, I didn't quite catch that. Is that from the room? It was a little broken up.
Maybe I can restate it a bit louder. He said the model you seem to have for customers is a dedicated core. CPU is dedicated to you. Could you change that model?
So maybe I should start by saying that the hypervisor does not pin a VM to a specific core. 1 second you're running on one core, next second you're scheduled on another one. Would I change that? Yeah, probably I would. So that we have a better sense of what's available, right? I'd love to have cores that are just, that we know are idle, so that 1, we can turn them off and save on idle power. 2, the telemetry becomes way simpler to identify and track utilization of these VMs that we otherwise have very little insight to. But so I don't think I actually answered the question.
I think the issue is what is the customer profile or customer, what expectation you set with the customers? Are they told they have the equivalent of a dedicated CPU?
Yeah. That's
Right.
the idea. Yeah, when you buy a VM, all this stuff is under the hood.
But you've already said that's not what actually happens, right? Because VMs aren't doing scheduling, right? They're not just pinning machines to core. So there's already a disconnect here. I'm just wondering why it's a problem to just let users deal with that, I suppose.
I'm not sure I fully understand kind of the point you're making, but I would love to understand it.
Peter, maybe we should do this offline because we're down to the last 10 minutes or so of the talk. So yeah, we can continue this conversation. I'll introduce you to the questioner in here.
Okay, 10 minutes. Geez. All right, I'll move very quickly and skip a lot of stuff.
No,
Just talk first. More coffee.
Okay, energy efficiency very quickly, right? It's the amount of computation we do over some amount of energy. This is really different from the typical data center metric, which is PUE, power usage effectiveness. This is what typically data centers people think about as the total amount of the power the data center consumes divided by the IT power, the power that the servers need. PUE really just obfuscates. It treats server power as a black box that we can't change, right? And tries to reduce the other overheads, like having to cool those servers takes a certain amount of power and so on. Tries to reduce those as much as possible. Energy efficiency focuses on actually opening up that black box that is the server and trying to reduce the amount of energy that it takes to do a unit of computation. Okay. Power proportionality is sort of a very crucial aspect of this. It's not like a really difficult concept to understand, but I drew it out anyways. Over the course of 2 days, our CPU utilization might look like this graph on the left, and our power is going to be something like this white line on the right, much less dynamic than the utilization. And that's because we have all this overhead coming from idle cores, right? Idle power usage. Just keeping things online requires a lot of power. Ideally, we'd be somewhere down here where the profile of power follows exactly the utilization, right? And I think we want to invest a lot of effort as researchers to improving this white line and moving it closer to this orange one and saving all the energy that's in between these lines over here. This is just an illustration, but it's not that different to what we see in the data. Okay. One way to try to do this is to manage processor C states. C states was something that I wasn't aware of until I joined Azure and all the architects taught me about them. At a high level, every column here represents a different processor state. And the further to the right we move, the lower our idle power. Okay, but we end up turning off various things in our processor. Why don't we do this all the time, right? Like when we're idle, just jump to C7. Well, it's because it takes some time to switch between these states. Oops, where'd it go? There it is. This, it depends on the processor, so we're not giving exact values here, but it takes time to switch between states. Not only that, it takes energy to switch between states. And so I think a lot of people have looked at managing these states to improve power consumption. And I think this is still an active area of research, even within our group. You know, one of the benefits of working at a large cloud provider is that we have a ton of data on a lot of very diverse workloads. And so we might want to try to learn from that and use that to our advantage to maybe predict how long the next idle state will be, and then go to the appropriate state in the meantime. Okay. Still a lot of opportunity here, especially when we look at the data center scale. Forget processors. Why not just turn servers on and off, right? This is kind of easier than it actually sounds easier than it is. in practice, the system has not been built to support this. We assume that every server will be on all the time, right? And if we turn one off manually and then have to restart it and add it back into the pool of servers that we decide to allocate VMs on, it's like a process that takes hours. Fine, we can engineer that away, but we have to convince the right people that this makes sense. It's actually hard to plan to have an empty server, because if we place, say, 20 VMs on a server during the day, there might be only 1 or 2 at night remaining on that VM, but that means we can't turn that server off, right? So what recourse do we have? We can move them to a different server and then have an empty server we can turn off, and that's called live migration, and that's super painful, right? It's hard to do, by the way. We can do it, but it's hard. It takes a lot of effort. A lot of workloads don't allow us. They say, no, we're not live migratable, don't touch us. And so while kind of might have a lot of empty cores, we don't have a lot of empty servers. But if we found some way to support kind of actually freeing up a server to make maybe live migration less painful, it would be fantastic, because then we can take advantage of this. Another idea is to look at not the servers, but the network itself also has a huge kind of variation in how utilized it is over the course of a day. So why don't we turn parts of the network off, right? We have a ton of redundancy in the network already for reliability reasons. Why don't we power down ports and save energy that way to make the network power proportional? Because from right now, from my understanding, and correct me, networking people if I'm wrong, but the power usage of a network is relatively flat, regardless of how much work it's doing, how many bits it's transferring. I've talked to some networking people about this, and they say it's kind of hard because you need to reconfigure things as you turn them on and off. And we already know how to do that because we recover from natural failures. And this is just a planned outage, essentially. And it might be easier because we have programmable switches now as the default in our data centers. No one is looking at it, as far as I can tell, at Azure. I've seen some academic work on this, and I'm excited about it. It'd be great if that work was sufficiently developed to convince data centers to start caring about it. Renewable energy, maybe I won't get very far, but I'll get to this point. This is my favorite. Reminding you of the strategy that Microsoft has, where currently we buy as much per year as we use. In 2 years, we hope to actually have built as much to cover as much as we use. So it's a marginal impact on the world's grids rather than borrowing from existing resources. And by 2030, we actually hope to do that from the same time and from the same grid that we draw from, right? And the right here just shows one of the many announcements we made about partnerships with solar panel companies to install crazy amounts of capacity. This one is 2.5 gigawatts of solar panels over the course of probably a decade. Yeah. The problem with this 100-100-0 goal is that it becomes really expensive once you start to creep towards 100%. And this is a graph from a report from the Rocky Mountain Institute, which actually looked at workloads that resemble data center workloads and calculated how much money you need to spend on renewable capacity like wind and solar plus battery in order to meet it 100% of the time. And while it's really cheap at the very start, right, you could, just by building out wind power that happens to align at times where you use that power, you can cover about 30% of your power that way, energy that way. And then you have to start building a little bit of more solar, which is a slight tad more expensive, and you get to about 50%. And then that number skyrockets because you need to start storing that energy, right? And it's almost asymptotic towards the end here. This is only 90%, okay? 100% would be off the screen. And at 90%, on the right here is a breakdown of the capacity of each one of these needed to essentially match 90% of the energy, and a huge portion of that becomes energy storage, okay? This is really expensive, and if we want to get to 100%, we can't be a static load, right? We need to find ways for our power to be more dynamic. or to increase the amount of power in the grid that we draw from to be more renewable as kind of like a freeway. Rather than building our own stuff, maybe we can interact with the grid in a way to help us get part of the way there, so that we can rely on our own stuff, but when we can't, we can draw from a grid that's much more renewable than it is today. So here's a project that I'll describe. It's about a grid interactive UPS battery. So we have these huge batteries I mentioned that act as a buffer between the time that we have a failure and the time we need to turn on a generator. Otherwise, those batteries do nothing. They sit there. They're active more during maintenance cycles when we check to see if they work than they are to actually provide the benefit that they're there to give. Okay. So one of the ideas was, hey, let's use them to offer services to the grid, things like frequency control. And this figure on the right shows what frequency control looks like. Grid frequency, we want it to be around 50 here in this figure. When it starts dropping and it reaches this threshold around 49.7, the UPS might kick in, and the load that this grid would see from this building in this case would drop significantly, because roughly 30 kilowatts of it was covered by the UPS. The UPS just charges not directly into the grid, but offsets a piece of our load, right? And when that frequency climbs back up over time, we slowly decrease the amount of discharge we do, and our load, as the grid seizes, would increase. This is actually a system that we have built a pilot project for and plan to deploy on a wider scale. The pilot is currently in Ireland. And Ireland is this magical place where every data center or every cloud provider wants to build data centers there. It has great proximity to the EU. It has very reliable grid, a very skilled workforce, which apparently is really important, right? There's like a shortage of data center technicians out there right now. We need to build in places where we can have technicians that work in these data centers that know what they're doing. It has a great climate, right? It's cool for a large portion of the year, so we have to focus less on cooling. And it has very great renewable penetration, like more than 35% wind power. Data centers under competition to essentially begging the Ireland utilities to let us build there. Having a system like this that actually makes the Ireland grid's job of maintaining its frequency easier gives us a competitive advantage to grow in a place like Ireland. Okay. So we're hoping that this kind of grid interactivity, this is just going to be the start. We're looking at more ways to find ways to be more interactive. And I hope that in 10 years, we'll see data centers that are very actively participating in the local grids with the flexibility that they have, right? All these workloads don't need to be on all the time. I would love if we can shift away from an on-demand cloud model to something where every workload exposes the flexibility it has, and we charge them less money the more flexible they are. And then we're able to use the workload itself as a lever, not just the batteries that we have, to participate and help the grid be more reliable and help the grid increase its penetration of renewable energy. And it looks like I'm at time. So I'm going to skip ahead to, oops. You guys see this?
Yes.
Slide 33. I'm going to skip ahead just to the very end. All the stuff I talked about, kind of currently in the works, there's some opportunities there, but there's also this huge change coming. AI is this huge workload, tons of hype right now, it's mainstream. You see funny articles like this one on the right? People talking about AI wars, etc. There's a huge change when it comes to cloud capacity. This huge workload needs a different type of hardware. It needs its accelerators, and accelerators are very, very power hungry, right? A single GPU consumes 400 watts of energy, of power at full utilization, and these servers have like 8 of them, right? And we want to put these very complex, large models into every product. Not just us, but a lot of companies want to integrate AI. If Azure is going to be the platform that allows people to run their AI workloads, it's going to explode. It's going to have to grow significantly. I can't say by how much, but there's studies that we looked at, and it's a huge opportunity for us to relook at how we're designing these data centers to be more flexible so that we can actually unlock capacity, power capacity in places that we care to grow in, right? And AI has some nice properties, especially for long training jobs that can, it's okay to turn them off for a little while because they're running for months anyway, so what's an extra day? And they also have frequent checkpointing built into the workload. So we can take that into account because we can turn the machine off and it hasn't really lost that much state, right? It doesn't have to restart from scratch. It has checkpointing built in. Food for thought when we're thinking about how to redesign data centers for the next 10 years. All right, thank you. I'm sorry I went so close to time, but hopefully there's time for a few questions.
Yes, are there any questions in the room here?
Sure. Yeah, thank you for the talk. On the last point, and also kind of on the first point that you made. So kind of the question connects the two. Can you hear me okay?
I can hear you almost okay.
I'll walk. So in the beginning of the talk, you said that you only share what you're allowed to share because a lot of data is private. Right? And so I was wondering, what is the way to get some of this data out? And specifically, I have recently looked at the question regarding your last slide, the AI workloads. I was interested in split between training that you mentioned and inference that you didn't mention. And apparently inference is actually often overlooked, but it's actually taken a lot more of the workloads in the data centers. And there is almost no data publicly available about from big cloud providers like Azure or like AWS that shares the actual numbers of this split. There might be good reasons, but I was wondering if there is a way to fish this data out somehow.
So I would love to tell you to just simply come talk to us and we'll give you everything you need. In practice right now, there's so much proprietary nature to all this stuff because of how core people think it's going to be to the business that even I'm not allowed to see some of this data. Okay, so I think a year from now, it'll be different. But right now, so many things are proprietary, under wraps, tented projects. I have to go through like 5 levels of people to even talk to OpenAI, right? A partner of Microsoft is almost impossible to reach. So hopefully sometime soon, this will change, but you might have to be a bit patient. I'm sorry, that's not a very promising answer, but it's kind of as honest as I can make it.
Thank you.
Yeah. Marco has a question, looks like.
Yeah, thank you. Yeah, so unfortunately we skipped over some of the slides, but I wanted to see if you had just a couple of minutes to cover the part about a phase free, where you were going to hint that you might do some work to extend the server's life cycle and perhaps building them differently in light of that. Can you quickly address that?
I can. So there's one major point I wanted to share on that note. So publicly, Microsoft says that we assume the minimum lifetime of a server used to be 4 years. And then we kind of write it off. And then recently we changed that to 6 years because these servers are lasting longer than we expected and they're still useful. Don't take 6 years at face value. In practice, those servers are going to be lasting a lot longer. We see servers that are 10 years old in our fleet. As a business, the cloud is not super mature that we have a well-defined policy for how we decommission these servers, right? Stuff that we're using, like from the first half of Azure's life as a product, right, is still useful to us in 2023. If you're looking at doing work on improving server lifetime, we should be looking at being much more ambitious than, say, 6 or even 8 years. We should be looking at 10 to 12 years, extending server lifetime to those points. And at that point, you see really interesting things that we start to care about, right? One is, where do we find the parts to replace broken pieces, right? Because our vendors, decided that this stick of RAM was now obsolete. It's DDR3, we don't do that anymore. We're on DDR8 or whatever it happens to be. So we need to be some thought around how do we run maybe on servers that have like half of the amount of RAM that they used to, that are old, right? And probably have less than everyone else that compared to a new server. Other things is, how do you create platforms that can choose where to send work, right? In a very heterogeneous setting where you have servers that are 12 years old, servers that are 1 month old with very different properties, right? They might have very similar max frequencies on their CPU, but chipsets would be different. The throughput on various workloads will be different. And so we're scheduling work over these heterogeneous systems that we need to understand how work matches to different hardware, et cetera. Those were going to be the main points on that note.
All right, thank you.
Sure, I can't see this. Is anybody else online who has a question, or?
I don't think so.
Okay, and I think there's none in the room as well.
Yeah, I just have a question about, because when you talk about using the overcapacity that you have scheduled for outages, for computation, you said if you have capable jobs, then you can freeze them, and therefore if there's outage and you were using 80% of the server but must drop it down to 70, you can always just pause some jobs. Whereas for the batteries, when you start using them as a grid UPS, you suddenly have a battery that's 70% capacity when it's supposed to have 100. And if it takes, I don't know, half an hour to run under the generator and the battery, minutes, you said, and the battery is supposed to last exactly that long, how can you afford then like using a bigger battery than you need to, right? Like this is suddenly a different kind of you are sacrificing the reliability when you talk about this.
Yeah. The answer that we've come up with so far is to build a slightly bigger battery. Essentially, when we participate in grid frequency control, this is for very short durations, typically seconds, rarely minutes. And it's outlined in the contract, right? We're not going to be discharging forever. We're going to be discharging up to a certain amount, because any further beyond that would affect the reliability of our data centers. So we're not going to agree to that. What we do actually is build out a little bit more energy capacity in our batteries to create a buffer, right? We have all the investment into the power capacity to be able to discharge a lot of power, and then investing in kind of like a little bit more energy capacity. Believe it or not, these people treat these things as kind of two different parameters, right? Investing in energy capacity is actually relatively cheap. So in that way, by essentially building a slightly bigger battery, we avoid it, but it still makes sense to do it.
And they don't, because normally they would build the batteries, but because you have already the overhead of this high power infrastructure, that's why it's cheaper for you to offer this service.
Yeah.
Okay, we are a little bit over time, so let's call it a day. Thank you so much, Fiodar.
Thank you. I'm glad to have you guys as an audience.
Great. And yeah, thank you so much for waking up this early. So we'll bring this to an end, and the recording will be on our website soon. So thank you.
All right. Thanks all.